Jak wspomniałam, to typowany Python nie jest czymś, z czym się spotkałam od początku pisząc w Pythonie. Mówiąc szczerze, wydaje mi się, że to jest temat ogólnie, który dopiero wchodzi, więc przełączę się teraz na angielski, bo prezentacja jest po angielsku, natomiast pytania później bardzo proszę po polsku też. Okay, so let's get going. Type Python, or what I like to call Python++, because to be honest, for me it seems like almost totally different language altogether. I'm calling it Python++ specifically, not just because it's something more than what Python used to be for me, but because it's something more in a way that reminded me of these old days back in the 90s, in the 2000s, when C++ didn't have all that heavy template magic around it, and it was more like C plus object-oriented programming. So it was basically adding something to C that C was clearly lacking, and it was exactly what was needed. So in case of Python or type Python, for me that was exactly what I saw lacking in Python, and what made me suspicious, what made me a hater of this language, and what made me let's say that each time when I entered my PyCharm, my heart rate slowly needed to fall down to the basic level, because I've already needed some coffee to to feel okay with using that technology, and I still have technologies that I use and still experience that. So okay, but I told you already how it started for me, but how it started from the other end. How was it from Python's perspective? Well, first I will tell you how it started from the Python perspective. Then let's talk a little bit about what was one of the biggest issues for me, which is classes and object-oriented programming regarding this topic of type Python, and how it differs from what you might know from standard Python. Then about a feature that, to be honest, is one of the killer features for me, because it is lacking in many excellent statically typed programming languages, such as Golang, or even C++ for a very long time, which is unions that I knew from Haskell. Well, Scala has them in the newest versions, but was also lacking them for a very long time. Then I want to talk to a little bit about some more advanced features that are also lacking in some languages, but are generally more mainstream and more powerful. Then about total overkills that you usually won't even need, but are super useful when you want to move your old Python code to this excellent Python++. Because obviously you didn't, you probably didn't follow all the design patterns of typed Python. So now we need to, like merge the two worlds together. It's just the two. I want to show you just the two simplest tools for that. But there are obviously many more. And in subsequent versions of Python, each version, I think, more and more goes deeper and deeper into types, and improving typing system further and further. And the last thing that I will show you is a practical example to how to merge all these features together, and show you why exactly it isn't just some little extra, and in fact it's a wholly new experience in coding in type Python, and you can't really get that when you're using just your plain old dynamically typed one. Okay, so how it started from Python perspective? Well, lots of people had experience similar to mine, so they didn't really like the fact that in Python, I see how the arguments are called, but not necessarily what they actually are. A lot of the time, it wasn't that I needed precise type. I just wanted to know what, just, get the basic idea what I was expected to do with that function, because just getting a number of arguments is not much really. So if the function has good documentation, obviously I know all those things. In Python community, there are many great applications that have excellent documentation with all of that. So what I think happened is that somebody sat down and said, hey, we have all those good practices in writing documentations and tests and all of that stuff in Python. And we've always been saying that it's duck typing is great, etc., but in fact, in some cases, in many cases actually, we do expect some types or some interfaces to be implemented. Well, we usually do actually. So why do we need to just go into the docs to see that? Why don't we have it as a part of our language? But obviously we need backwards compatibility, so it's optional, right? So that's probably what happened with PEP 484, which was I think the first one that introduced the what now is type Python, which really focused on signatures in functions, but it added just a little needs here and there for type comments, which allowed you to declare type for some variable inside of the function, but was generally very function focused. Then it was quite perceived quite well, and contrary to what might be expected in Python community, received quite a bit of attention. So there were subsequent PEPs. So starting with, I think one of the next major ones was PEP 526, which introduced typing to object-oriented programming in Python, because obviously, if we support functions, why don't we support classes? Which is great, to be honest, because it may seem like a small thing, but we'll see in a minute that it's really not. Also turned most of the type comments, if not all, I think, into proper grammar in Python. It were just a little changes in the Python interpreter, so not a great problem, not that much of a deal. Pretty easy to implement, pretty easy from the design perspective. So, the greatest thing is that it wasn't planned all along, and which would take much more time, but it was happening in small steps as people saw that it works pretty well, and what is lacking still. Okay, but we have types in our code, and what? Well, it looks nice, certainly, but what can we do with that? Well, there are some tools for that. For instance, we have, and I think it was pretty quickly adapted. MyPy is a tool that lets you check your types. So for instance, if you call the greeting function with an integer, MyPy will return you that it's a type error. Of course, it's static analysis of your code. It doesn't occur during the runtime. But as you will later see, Python is a little bit different from many, if not maybe not most, but from many statically typed languages when regarding types. It's a little tricky concept because it wasn't always baked into the language. But without further ado, let's just dig into specific problems, some details on how to use this thing and to why is it so nice, in my opinion. First, let's go into the second example, actually. So PEP 5, 2, and 6, which introduce class fields. Well, it's certainly nice to be able to quickly, scan the fields the class presents, especially if you have quite a bit of them, and the initializer is well, not trivial, because if you just set them, if you have just arguments to the initializer and then set them into your object, well, that's not so bad. You do have a little bit of code repetition, but let's be honest, it's not such a problem. It becomes a problem when you have it very, very long, and it might not be immediately obvious which parts of those arguments are actually fields of your class, and some fields might not correspond to an argument in your initializer. Of course, good docs always had that. Good docs always declared what kind of fields, public fields, of course, your class has. So your users were generally used to the overall idea. So in this case, typed Python lets us additionally, it's not a replacement for the initializer. It's what you might include as an additional thing. Declare type for your field in your class. In this case, we have a default initializer, but mind you that it's still Python. So it's not exactly the same as the default value in other languages, because in this case, it's a static field in your class, which you can also override, mind that. So if we take that field foo from the class itself and not from the instance, we can override that default. That's not necessarily what you usually want, but overall, in general usage, it works pretty good. As you can see, you can use it just like any other. In fact, it's not really an interesting example very much, because you just add that type annotation to your static field, which doesn't bring that much. Okay, but as I said, it's a static field. So what if we really do mean that it's a static or class field? Well, typing system lets you make the difference between what is a static field, but in general, it should be treated as the default value for instance fields that are set in the initializer. Not a very good practice, but you can use it that way. And class variables that should be used as class variables are not overwritten in the initializer and stuff like that. So we simply import from typing what is called a class variable type, which is a generic type. You can see that type Python uses square brackets, just like many other languages, including Scala, for instance. And you can access this as expected. But if you really want something like structures in C or case classes in Scala or stuff like that, you probably know what I mean. Some simple container for data that is a class may have some behaviors attached to it, but in general, its initializer is very, very simple. In this example, it's trivial, even it doesn't do anything other than set fields. You can use two libraries. One is from standard library, it's called data classes, and the other is Atrus. I personally use Atrus because it has more features, but data classes should be enough for most cases too. As you can see, we don't declare the initializer at all. We only use the decorator data class, and this decorator creates the initializer based on the fields that you declare. What is interesting is that at runtime, it becomes exactly the same as if you have written it by hand. So you don't get any performance penalty for using this data class feature. And what is more, you get some additional nice stuff, because as you can see, well, obviously we can initialize our class. We can make a new instance of it with some argument of the type mypy and pycharm, and all of the good tools for typed Python will obviously recognize if we use the right type or not. But some additional nice touches is that, for instance, we have comparison. So as you can see, we can compare two different instances, and the comparison works as expected for structures in C or case classes in Scala, and etc. It's not just equality, though. We can also define ordering, hash, and multiple other features. We can also tell data classes or attributes that we want this class to be frozen. So when you create it, it won't be modified ever again. Sometimes it's useful. You can define it as slots class. If you know slots, it improves performance of your classes in case you have many objects, because Python in general stores your classes as with a dictionary inside. But if it's slots, it's just a tuple, which takes much less memory. So so you basically add just a half a line of code, and magically you have all of your stuff in slots. And what's more, data classes work perfectly well with inheritance, even multiple inheritance, with keyword arguments to the initializer. You can mix initializers and data classes, so you can have data class with all of the goodies that I mentioned, and still define your own initializer if you want. You can define converters. You can define default values, default factories of the default values, validators for your values. So if you have a initializer, you can then additionally add a validator to the field, so that your field gets checked not just by type, but with some runtime checker. For example, we only accept integers, but they need to be positive and stuff like that. So lots and lots of features. And it's not like you can't use libraries like that without types in Python. You can actually. These solutions predate typed Python, but they became much easier to use since typed Python is here, because in the simplest cases, they make it trivial to define such structures. So in fact, you could say that in typed Python, we have a different kind of a class, which is data class. We also have other different types of classes. So for instance, we have dictionary class, which is a class that the runtime representation of which is a dictionary. So you use dictionaries, but they are type checked and generally treated as if they were classes. So we require them to have some keys present, and these keys should be of certain types and stuff like that. So pretty nice thing. Again, quite a big topic. It's quite a broad thing. So you can, I think you can already see why it catched my attention when I first realized what types in Python can do for me. And it was just the beginning, because next I saw that in Python I can declare a union of two types, which means that I can expect multiple types for the same argument of a function, or for the same field of a function, or return multiple types from the function and stuff like that. So for instance, in this example, I have graph from matrix with which is some old function that didn't use type Python. So it just had that documentation and said that the second argument can be either a string or a Boolean. The default is Boolean, it's for false, but it can be a string, and if it's a string, then it's blah, blah, blah. And if it's a Boolean and the Boolean is true, then it's the same as passing the default value of the string. Something like that. Maybe it's not as common in Python, but for example, in R, it's a very typical design pattern to use it that way. And in some Python libraries, especially in data science, we have it as well. So if I have MyPy or PyCharm, one of the big advantages of using unions is that typed Python is contextual. So if I use if instance and check which type is that variable, then typed Python for the body of that if statement will already know which one is that, because it already checked what it is or is not. So for instance, I can check that it is a bool, but I could also check that it is not a string, and it would be the same, just the branches would be swapped. Which is great, because really I can have all my types checked at compile time, and in these few cases that the type isn't immediately obvious at runtime, I can check it at runtime, and still it corresponds to static typing. As you can see, the branches have the type narrowed down. So that's why I said that the relationship between runtime and compile time, let's say compile time in Python, the static time is has some twists to it. It's a little bit similar to how it is in Kotlin, for instance, if you know what I mean. There is a feature like that in Kotlin too. But let's be honest, writing union isn't the best thing in this world. So as I promised, each subsequent version of Python, of type Python, has more and more goodies for you. So you had unions as a generic type that can accept any arguments. And you had this old ugly is instance, which accepted a tuple. And now in Python 3.10, you have brand new syntax for OR operator for types. And as you can see, it also works with is instance, which is great, because you can have you can assign some union to an alias and then check is instance that alias, and you don't even have to worry that this alias is a union and oh my god, how do I check at runtime that something is a union? Well, in fact, it's pretty trivial. It's you could do that in previous versions of Python too. It's not super difficult to get the types of type members of union if you have the union type available. So why not bake it into the language itself? You could wonder how it works, considering that in Python 3.9 I have 3 arguments to union, but in Python 3.10 I have 2 calls of the OR operator. So it's not one function that accepts 3 arguments. It's one function that accepts 2 arguments, and then the result is passed to another call of the same function with the third argument. Well, in fact, it always worked that way. So a union of unions is flattened to a union, and if some type is repeated, then it's when the union is flattened, then it's removed. So the union, essentially, you could say it works as ordered set in typed Python. So you don't really have to worry about that. There will be some code duplication, that your runtime will blow up because you will have a check for string type, for example, for 3 times no. It will all boil down to as if it was a set. But what if unions aren't enough? What if we have, which is pretty typical for Python, what if we have a function that accepts some type and the result type depends on what you passed? So for instance, we have, we pass a list, let's say, and if we pass a list, it's a list. If we passed a set, it's a set, something of that kind. So in other languages, we would use generics for that, but obviously it would be a little bit complicated for Python to add generics. So another thing was added, a little bit different, which is a type variable. So in general, you could say that you declare something as a type variable, and then you use it in a signature as a value. But because the declarations of that variables have some additional rules to them, therefore PyCharm, MyPy, and stuff like that can know at static or let's say type check time what the type var is. So in this case, it's just any type. But you could add bounds. So for example, you could say that it must be a container, or that it must be one of 3 types exactly. And it's the same one, you know, it's not the same as union. So if in this case, we have unions here and as input and output, then we know nothing about output. But if we have a type var with 3 variants, then we know that one of these 3 is allowed. But if we use one of these 3, then the result type is the same. So if we have, for instance, list or set, and the output type is the same, and if we pass a list, then type checkers know that the result type is also a list. Okay, but that maybe wouldn't be that useful, but it becomes more and more useful when you realize that you can parameterize your other types with that type var. For instance, you can easily write repeat function, which takes value and creates a list of the values of that type. Or you can create head function, which, to be honest, I always feel like it's so lacking in Python. Little things like that that are already available in most functional languages. Head function which accepts a list and returns either the first element of that list if there is one, or none if there is no elements in the list. Okay, but that's quite a powerful thing, because in fact we don't have anything of type T here. We only have list of type T and optional of type T. Type T is wholly inferred in the static time, in the type check time. It's not available anywhere at runtime. You don't, it doesn't have any cost at runtime whatsoever, because it's not available anywhere. It's just that you provide a list. The type checker says that the list only contains one type, for instance, let's say string, or strings and instant says that it's a list of unions of string and int. And then you apply it to the head function, and it knows, okay, so if it was a list of union of string and int, then the T type is union of string and int. So the result type is optional union string and int. Optional is basically union of something and none. So as you can see, we do have some type pattern matching in type Python. Pattern matching in general in Python is a very late feature. It is only available in not in full support yet, but the very beginning of pattern matching at runtime for Python is since version 3.10. So type Python in fact has some features that runtime Python only tries to catch up now. So type system has some functional goodies that that runtime Python still doesn't have, which is nice for me because type level programming is my kind of a thing, and it's very, very useful in writing compilers. That's why I use this example. Okay, but what do we do next? We again move it to classes. So if I want to have a method in a class, of course, I can use type vars too. So I can have a generic method, let's say. But what if I have a class method, which is kind of as if it was generic, but by the type of this class? So for instance, I have an int box, and I have a, let's say, helper method to construct the int box. But if I have a special int box, which is a subclass of int box, I would still want it to return special int box, not int box. Well, for that, we have, once again, a little bizarrity, which is the difference between the type and the type of type. So just as before we had that contextual typing, in here we can, just like we can say that self is of type self, we can say that class of self, which is usually called CLS in Python, is of type self. So it even reads the same in runtime Python and in type Python. It reads type of self. So pretty intuitive, actually. And thanks to that, you can declare stuff like for CLS of type self, return self. So if you pass me the class special int box, I want you to return the instance of special int box. And it works. Okay, but being in classes and topic and stuff like that, I've already told you about some generic types in type Python. You can also declare your own generic type using using generic feature. And in generic feature, you can declare the arguments of your generic. In this example, we don't have int box anymore. We have a box of any type. Of course, it's not the only way to have a generic type, because you can always use one of the types that is already generic and just derive from it. So, for example, such a type is collection, sequence, list, mapping. Mapping has 2 arguments, by the way. And mapping is also an interesting example because it also shows that the relationship between generic and type var is a little bit tricky because, for instance, you want to have different rules for the first argument in mapping or in dictionary than for the other one, because one is a key and one is a value. So you obviously get all the features from functional languages, like you can have covariant and contravariant type variables and stuff like that. So it's pretty mature, I would say, and I was quite surprised because it's more mature than many other generic type systems I saw. In fact, I think that even in C++, I would need to have workarounds for some of these features, and nobody would say that C++ has poor support for generic programming, would it? Okay, but what if generics and type vars and type of type and all of those things and unions, if they are still not enough, we are still struggling to move our legacy code to type Python, because we have some function that has like completely random rules regarding types. We just write in the docs that if you pass a string here, the result type is any. If you pass a bool here, the result type is, let's say, none. it's not that difficult to think of such an example, because we can have a function which may or may not additionally, when doing something, either return some additional information or not, because maybe you don't want that information to be computed alongside the primary thing, and so why would you care? Well, we could use optional, of course, but in such a case, the user would be confused as to when it's known and when it's not known. So, what's more, we have so many design patterns in Python. So even in the standard library, when it's not so clear just to use for type var or union to express all the information that the docs would give us. So what do we do in such a case? Well, we do have what is a tongue about among the features of type Python, which is overload. Overload basically lets you declare any signature of a function that you want, and then once you know that once you declared all the signatures that you want, then you declare the function itself and its implementation. So, okay, how does it differ? Well, you can declare any signature whatsoever, and type Python static analysis tools such as MyPy, PyCharm, and stuff like that will simply match those signatures against the call of your users. What's more, PyCharm will also suggest the users all those signatures at the same time, which is quite nice, because they see it without reading the docs. It's much more clear than reading the text that provides examples of how to call it and stuff like that. So just as I said, you can have, for instance, overload that changes the return type depending on if we want to extract some field from this or not. It's quite a typical use case, I'd say. What might be a little bit surprising is that you can also provide types for the implementation of this function, and these types won't be visible to the user. So for the user, they will see string to none and string to any, not string optional string to none. It should be optional any, I think. Okay, but even if that's not enough for you, because for instance, you have something like open, because in Python we have the beautiful function open, which has a string argument which only accepts a few different possible values of string, but it's still string, and returns different types depending on or possibly different types depending on what string it was passed. Well, even for such a case, Python has some solution, and that is quite a unique feature among programming languages that I've seen in the wild very, very rarely. It's one of the few to actually support that. And this is literal type, which once again blurs the line between types and runtime values, because now we can get a separate type for specific literal, specific value at runtime. So for instance, we have a separate type true, and separate type for false, and separate type for string hello world, and stuff like that. So you can easily imagine that we can overload our functions depending on literal R or literal W. So yeah, it works. It is just what we need to, of course, when used with overload, to declare the type of open function. Okay, but open function already exists, so what do we do with that? Well, it's not a problem, because in Python you can, in type Python you can declare what is known as stub files. So files when you only have those overloads present, and they are, let's say, attached as additional information for the type checker. And for instance, you have a standard library with open and all of those. And in a separate file, you have the type signatures of functions for that same Python module. So for instance, you would have those signatures for open function, and you can do that with your code too. So even if you don't want to modify your original code and add those overloads, you can still benefit from typed Python because you can add overloads in your stub file. So you can do that even if you don't want to modify your file. And as you can see, it works pretty well because you can overload even by literal and by the type of that literal. So in this case, it will be different if we pass a runtime boolean that we don't know if it's true or false, and it will be different for true and for false, respectively. The type will change. You can, of course, have type of a literal assigned to it as you assign it to a variable. Sure, no problem. So you can have a variable of type true, of type literal true. You can have something of type literal R, R, W, and W. So it's something like a union. It accepts either of those literals. And in the current version of type Python, it will also flatten, just like union. And there are basically no restrictions as to what you can put in the literal. So no problem with that. Okay, so why is it Python ++ exactly? Right? We saw many features and stuff, but why is that great that I now am Python lover and Python enthusiast? Well, all of that stuff that I brought up about blurring the line between runtime and types is really shallow compared to what I'll tell you now, that these types, in fact, are available at runtime. They are just not checked at runtime, but you can just write your type checker yourself. It's not that difficult because you can access type information of any structure that you use. So for instance, you can get all the types in a data class. You can get all the types in your unions. So what do we do with that actually? Why is it so useful, and why is it useful in writing compilers? Well, at IBM, we have some UI with some JSON format that it generates, and we want to parse that and generate some code based on that. So let's say we have a document that has multiple graphs on it, and one graph is the primary graph that we start in. Of course, the document may have some ID, maybe not. The graph has obviously some ID. You need to distinguish the graphs between each other, and some nodes. Well, the node only has a type, which is a string, nothing special. But what is interesting, that nodes can be divided into models, model nodes and super nodes. Model nodes refer to some machine learning model or not, and super nodes refer another graph. So you can, have a graph inside of a graph, let's say, as a node. And we have on the right a structure that more or less looks like that. It has some primary graphs, some nodes, and stuff like that. And we want to parse it. So in standard Python, it's not that easy. It's not that easy. We would parse a dictionary and list and stuff like that. But we do know what the schema is. We could even generate that schema. Why do we need, for instance, JSON schema parser or something and then operate on dictionaries if we can simply operate on classes directly and parse classes directly, and additionally have unions and all of that goodies. And if we use all of those features that I've described to you today, we can get a fully generic function that accepts a type and JSON and returns every error was encountered during the parsing with full stack traces and etc. As you can see, it says that in graph, if graph of index 0 in node index 0, the type was special node, but we don't have such a node defined. And in graph 1, the node 0, it is a super node, but it doesn't have any graph ID. So it doesn't refer to any graph, but as a super node, it should. And of course, if there are no errors, then no exception is generated and the class is returned. So again, it also uses that type, similar to class methods and stuff like that. So as you can see here, most of the features that I've shown to you were used in this code, and in such a way it was possible for us to have a fully declarative description of our format as a hierarchy of classes, and any of our teammates can edit it without any problems whatsoever, because it's simply trivial to edit it. You just write this try parse once, and then it just works, and you can edit your class hierarchy however you want. So pretty nice in my opinion, especially considering that you don't have dictionaries all around. You have classes, the classes can have methods and stuff like that. It's a little bit trickier with unions, because with unions the parsing of errors may sometimes require some additional work for what is known as discriminators, but in the general use case, you don't even need that. You just will have alternative errors, like if that type was supposed to be A, then the error is something, and if B, then error something, stuff like that. So all in all, I call it Python++ because it allowed me to write my compilers. I can't even say that as in my favorite functional languages, because many of my favorite functional languages don't even have those features. I think Scala is the only competitor in this case, and to be honest, the Scala is has quite heavy runtime. So, and you know, why not use Python? It's so beautiful. Thank you, and back to you, Carol.